Imagine a huge outfit played by a perpetual number of stars, planets, and moons, all produced as a bound-together opening. In any occasion, there is one specific region of this assembly that has frustrated cosmologists for a truly long period: exoplanets. These are planets that exist outside our planetary framework, hidden away somewhere down in the Milky Way. You might be flabbergasted to learn that among the tremendous number of infinite objects, there are exoplanets so like Earth that the story strays away from in an unforeseen direction, particularly like a science fiction thriller. Experts utilizing the James Webb Space Telescope found something surprising from Proxima B, a sign so astonishing that it moved all through the educational fragments in research networks. It was named a potential technosignature, a signal so confounding and complicatedly organized that it might actually show the presence of a high-level progress. The collective heartbeat of mankind appeared to stop at the apex of a declaration that vowed to have a significant impact on our point of view on reality. Could that sign be the most clear proof we are not alone in the universe? Similarly, as rapidly as it seemed, the sign scattered without returning, leaving behind not simply a mind-boggling quietness, but also a maze of unanswered questions and unavoidable theories. Was it just a transient natural peculiarity, a consequence of grandiose movement, or something else entirely, perhaps a coded message or even a sign from an advanced, possibly unsettling human civilization? This single mission cast a sad remnant of uncertainty over Proxima B, touching off a heated conversation. At its center was the question: was it simply a transitory inconsistency, or part of a bigger, undeniably more bewildering story? This story, a woven magnum opus of our unfathomable quest, remains incomplete. The ink has not yet dried, and new parts are still being composed. This time, it isn't just traditional scientists but also Harvard experts who are driving a change in perspective in our search for extraterrestrial life. They're not just breaking down the signs and signals we've noticed up until this point, they're expanding the scope by transforming the James Webb Space Telescope into a high-level night vision telescope. Their objective is to look for artificial light sources, both in the weak and enlightened districts of far-off universes. Imagine recognizing the brilliant lights of a city, a metropolitan scene shining in the midst of the enormous darkness, alluding to the presence of a general civilization. As we continue to disentangle the universe's secrets, the quest for extraterrestrial life takes on new aspects. Rising above the short interest with Proxima B, our inquiry digs deeper into the secretive spans of space, driven by historic headways and a tenacious curiosity about our place in the universe. Persistent advancement in cosmology and space investigation has led to the discovery of numerous exoplanets with potential for habitability. Instruments like the James Webb Space Telescope, JWST, and ground-based observatories have significantly improved our capacity to recognize and study these far-off worlds. One particularly interesting field of study is the quest for biomarker signs of life. These markers could include atmospheric gases like methane or carbon dioxide, which under the right conditions could indicate biological processes. The JWST's capabilities go beyond fundamental discovery. Its advanced instruments can examine the atmospheric composition of exoplanets with astounding accuracy. By concentrating on light that passes through an exoplanet's atmosphere, scientists can identify chemical markers indicative of life. For instance, the presence of water vapor and other molecules like oxygen or ozone may suggest conditions ideal for life. A different line of investigation centers around the states of these far-off worlds and the search for technomarkers, which have gained momentum. These are signs of advanced civilizations apparent through artificial structures or advanced technology. Such markers may include superstructures like Dyson spheres, designed to capture a star's energy, or unusual patterns in radio transmissions. As we refine our observational techniques, the quest for technomarkers could uncover the presence of extraterrestrial intelligence, not just historic advancements but also global collaborations that are vital in the journey for extraterrestrial life. Collaborations among space agencies, research organizations, and private entities support our ability to explore space. Missions to Mars and other celestial bodies are powered by contributions from various nations, pooling resources and expertise to achieve shared objectives. Public engagement and education are likewise key, as the energy surrounding space exploration drives the future of scientific inquiry and learning. New advancements further improve our understanding of the universe. Advances in telescope design, data processing, and computational models enhance our capacity to detect and study far-off exoplanets. Cutting-edge space telescopes like the Extremely Large Telescope, ELT, and the Habitable Exoplanet Observatory, HabEx, promise much more detailed observations and deeper insights into the possible habitability of exoplanets. As we push the limits of our knowledge, each discovery raises new inquiries and areas for investigation. The quest for extraterrestrial life isn't just about finding alien civilizations, it's also about understanding the origins and diversity of life across the universe. It challenges our perceptions and expands our thoughts on being alive. The exploration of exoplanets and the inquiry for extraterrestrial life are dynamic, evolving fields. With each step, we edge closer to responding to some of humankind's most significant questions. As we continue exploring the universe, the potential for finding new types of life and grasping our place in the cosmos remains unfathomable, tantalizingly similar, yet frustratingly different. Proxima B may be Earth's twin, found 4.2 light-years away, but the James Webb Space Telescope guides our journey to comprehend these vast mysteries. Imagine briefly your mind traversing the tremendous, superb span of our universe, the Milky Way, home to more than a quadrillion exoplanets. To put this number in context, if each exoplanet were the size of a grain of sand, we wouldn't merely fill the Grand Canyon, we'd have enough to create another landmark on Earth, Grand Canyon 2.0, stretching for a monumental distance. Most amazing of all, around 20% of these celestial bodies are thought to be Earth-like in terms of landscape and environmental conditions. That means there's a 1 in 5 chance of finding a twin of our planet. And the story doesn't end there. Alongside these planets, there could be another quadrillion moons, hostile satellites like our moon participating in gravitational dances with their parent planets. If you somehow figure out how to find another body in space that harbors life or might potentially do so, the universe offers a surge of opportunities. Now that we have illustrated the immensity of this vast tapestry, it's time to present the showstopper, an instrument designed to uncover its various subtleties, the James Webb Space Telescope. This superb Sherlock Holmes of the cosmos, with its impressive central length, outperforms even the most advanced Marfan optics. We're not talking about any lens. Its 6.5-meter primary mirror is 2.7 times bigger than Hubble's. Imagine the best detail it can perceive, even the slightest gleam of a star billions of light-years away, and then explore the details of orbiting planets. What makes the James Webb Telescope revolutionary is in addition to its seeing power, yet additionally its state-of-the-art innovation, including forward sensors and spectrographs. These instruments can do considerably more than notice. They can investigate and channel the special light marks transmitted or reflected by heavenly items to unwind their barometrical circumstances, thickness, and, surprisingly, mass. Acting as a space specialist, they can determine whether a planet has water, natural mixtures, or indeed, even oxygen. The James Webb Space Telescope can respond to these inquiries, hoisting it from a basic spectator to a logical virtuoso. It's more than an improvement over its ancestor, Hubble, it's more similar to a quantum jump. If Hubble's disclosures dazed you, get ready for a certified explosion of grandiose discoveries as we expand our view across the immense region of the universe. It merits zeroing in on one explicit star in the amazing show, Proxima B. Since its revelation in 2016, this curious planet has stood out as a Shakespearean legend, loaded up with complexities and secrets, enrapturing space specialists and astrobiologists the same. What's the big deal? Overall, Proxima B is in a general sense in our cosmic neighborhood, simply 4.2 light-years from Earth. To place it in context, on the off chance that you could beat the all-universal speed limit and go at the speed of light, you would show up in under 4 years, about the same measure of time it takes for your most loved show to fall into reruns. Yet we should dig further into why this closeness is so critical. We're discussing a universe that traverses in excess of 93 billion light-years from one finish to the next, so finding a planet so close and thus promising for logical examination resembles tracking down a diamond in a heap the size of Mount Everest, a pearl that maybe holds mysteries about existence itself. In the amazing embroidered artwork of the universe, Proxima B is a diverse secret, offering us huge hints that could reshape how we figure out livability in life past Earth. It's not simply Proxima B's closeness to Earth that energizes researchers, but additionally the tempting signals that this planet isn't simply Earth-like, but maybe Earth 2.0. Proxima B sits easily in what space specialists call the livable zone of its parent star, where conditions are neither as well hot nor excessively cold, yet on the money for fluid water to exist. Envision cascades, wandering streams, huge lakes, and perhaps, indeed, even oceans as profound and secretive as the Mariana Trench. However, before we begin longing for heading out to Proxima B, we need to consider a few quirks. For example, a solitary day on this enchanting exoplanet endures an astounding 11 Earth days. Envision dusks that stretch into another day, gradually resisting giving way to noontime and sundown, making long hours that photographic artists would begrudge. While it sounds charming, it additionally has significant ramifications for its current circumstance and tenability. How might human biorhythms change in accordance with the examples of light and dark on Proxima B? Would we need to eat at least multiple times in a single day on that planet? Would we sleep the same way on this completely unique world? The vital components of life, as we realize it, would be tantalizingly comparative, however unusually outsider. Maybe nature is giving us a riddle enclosed by a secret, testing how we might interpret what makes a planet livable. You can't help thinking about how we can assemble exact, solid information about a world we have never visited. The James Webb Space Telescope brings all its ability like a Goliath Swiss Armed Force knife. It's more than simply a telescope, it's a modern research lab in the vacuum of space. On account of its trend-setting innovation, space specialists can notice planets as well as additionally dissect them from a perspective of logical instruments that would make CSI labs look basic. Utilizing progressed spectrographs, the Webb telescope can concentrate on the light communicated and reflected by these far-off planets. Each component or particle in a planet's climate ingests or radiates light at a specific recurrence. By zeroing in on these examples, specialists can play out a distant biopsy of heavenly bodies, deciding not simply pneumatic stress and thickness, but additionally the conceivable presence of mixtures fundamental for life, like water, organic carbon particles, and indeed, even oxygen. It's not simply cosmology, it's space crime scene investigation. We don't inactively stand by for signs to effectively contact us, we search them out, looking at the atoms and molecules that make up these complex universes. The Webb telescope isn't simply an eye overhead, it's an exceptionally specific research office, a specialist, and a vast criminal investigator all in one. It permits us to turn our speculations and theories about outsider worlds into strategies for affirming or refuting them, changing our comprehension of what could exist past our blue Earth. When you assumed you had uncovered the most strange layers of this huge woven artwork, the excursion is simply beginning. As we stand almost there of boundless disclosure, the James Webb Space Telescope addresses a signal of trust and progress. Its powerful instruments are intended to dive into the most unpredictable subtleties of far-off universes, uncovering parts of the universe that were already outside our ability to comprehend. The JWST's capacity to look at exoplanet climates broadens our excursion into the farthest corners of space, offering bits of knowledge not simply into whether these planets could uphold life, but additionally how life could arise under various conditions. One especially captivating part of this examination is the potential to identify biomarkers in the airs of exoplanets. These biomarkers, for example, explicit air gases or synthetic arrangements, could act as signs of organic processes. For instance, identifying a blend of gases like methane and oxygen could propose organic activity, as these substances often result from life processes on Earth. The JWST's high-level spectrographs can identify these inconspicuous signs in the midst of the boundlessness of space, offering another window into the potential for life past our sunlight-based framework. Besides, the quest for exoplanets has acquainted us with a variety of planetary frameworks with remarkable qualities. Some exoplanets have been found in parallel star frameworks, where two stars circle each other, creating complex gravitational circumstances. Others circle red dwarf stars, which are cooler and dimmer than our Sun, yet possibly equipped for facilitating habitable zones.